Hi, I'm Ahmed Daud, and in this session, we will discuss the computational complexity of decision tree regarding the prediction process and the training process. So, what is actually computational complexity? It is an important concept in computer science used to usually analyze how much our algorithm is efficient in terms of time and space, so that we can compare with other algorithms and we can analyze how much it is taking the time, how much it can take the time or space. In computer science, we usually use O notation for the when we are calculating some complexity. So big O is used to describe the time or space complexity of an algorithm. O symbol stands for order of. So here in that particular case, we will discuss our time complexity of decision tree. So first we will discuss the time complexity when we are predicting some new data point by our tree. Okay, that we have built. So we will continue with an example by considering an example so that you will get a more clear idea. So let's say at the start we have a data set which has m number of samples and n number of features, and m is equal to 16, n is equal to 4. So there are 16 samples in our data set and 4 features in our data set, and we have built our decision tree on by using that particular data set of 16 samples. So let's say we have built a decision tree which is very balanced decision tree. It means it is at each particular node it is splitting the whole data set into two equal parts. Okay, we are considering some ideal case so that we can conclude our time complexity uh, for the decision tree. So first, 16 samples at the very first node. We have split it into two parts, 8 and 8, then 8 into 4, and so on. So we have this type of decision tree. And now I want to see that whenever my new data point will come, how much it will take to predict the new data coming. Okay. So predicting a sample require to traverse log of m nodes. Okay, what actually it means? It means that uh, whenever new data coming point will uh, reach to that decision tree, it will check from the very start. It will check the one value of that coming data point that is at that particular node as a rule. Okay, there is a one decision rule at this position of that during the training of that decision tree uh, we have extracted from as the base of best split value from some feature. Okay, let's say feature 1 is less than 4.5. This is the decision rule at that particular position. So whatever data will come, it will first of all see that what value of f1 that coming data point have. If the value is less than 4.4 of the new coming data point, then it will move towards the next decision rule. Okay, and again it will check again one value that is present here as a decision rule, and on the base of that value it will move further towards the more down word node. Okay, then again check the decision rule and move towards the next node. And on the base of last decision node, it will then send the it will predict the sample that will be on which side, on the base of last decision rule, with respect to that terminal node is representing the class. If this terminal node, let's say, the representing the class 0. Okay, then it will this decision rule, on the base of that decision rule our sample goes towards this side and it will be predicted as a class 0. Okay, this is the process of prediction. So how many times we have checked our uh, new data point, how many times we have checked that, okay, against different decision rules. First we have checked at that position, at the very first position, then at that level, then at that depth, and then at that level. Okay, if you will calculate, you will get here the result that 4 means you have checked your new coming data point, new point, you have checked your new data point against the 4 decision rules, and then you decided the or your decision tree decided to predict the class or that new data point. Okay, so you can see that what 4 is representing here. 4 is representing here the depth of that decision tree. And how you can calculate the depth of decision tree when decision tree is balanced. You can say that log of base, because base 2, because it's a binary tree. So what number of samples, total samples we have, like m number of samples, this will be the depth of the decision tree, or you can say this is the prediction time complexity for the prediction. In our case, the m is 16, so our prediction time complexity for the prediction is equal to 4. Okay, so you can see that at each level you have checked one value just against some feature which was present in the decision rule. So as the number of levels our decision tree have, that number of times we have checked the values of our new data point. So the log of that number of samples present in our data set will be our time complexity for the prediction. Okay. So independent of number of features, whatever number of features you have, it is prediction complexity depends on the only on number of samples. Okay, whatever number of features you have, like 10 number of features. Okay, so when you are splitting here, you have 16 samples. When you are splitted into two parts, then two parts and two parts, you will get only the depth of 4 when you have balanced decision tree. Okay, so irrespective of the number of features, you can calculate the time complexity for the prediction process of a decision tree by just considering the number of samples in your data set. Okay, so number of samples in your data set that you have used for the training of decision tree. So this is for the prediction process. Now we will consider how much the time complexity for the training process. So when we are doing training on of the decision tree, what we are actually doing, let's say again I have considered here four number of features, n is equal to 4, and let's say m is equal to 16. 16 number of features I have considered here. So at each level, like this is the very first node, at each level we check the each value of each feature. Okay, each value of each feature to find the best split value. Okay, first we find the best split value of f1, then best split of f2, then best split of f3, then best split of f4. So for all the values of f1, that are 16 values, because there are 16 samples, so we have checked there. Then 16 samples checked for the f2, then 16 for f2 3, and then 16 for f4. So how many values we have checked to find the best split value at the very first node? 16 into 4, which is this one is m, this is n, which is 64. Okay, so m cross n number of split values you have checked that at that point. So at the second level, when your data is split into two parts, now you have here 8 number of samples. So 8 samples into how many features we have? Total 4 features. So 32 split values we have checked here to find the best split value. And again 8 into 4, 32 split values we have checked at that right node to find the best split. Again, at this position, we have 4 samples. So 4 into 4 number of features. There are 4 features. So we have checked here 16 number of values to find best split, and 16 here, 16 here, and 16 here. Okay. At this position, we have checked 2 samples into 4, 8 number of values to find best split. 8 here, 8 here, 8 here, 8, 8, 8. At the end, when you will calculate the total number of split values at each level you have checked, at the very first level you have checked 64 split values. At the second level you have checked the 32 plus 32, total 64 split values. At the third level again you have checked 60 values, then 16, then 16, then 64 times you have checked 16 split values to find the best split. Against plus is 64. So at this position again 8 plus 8 plus 8 plus 8 plus 8, and these are 3 to 5, 6. how many times? 3, 5, 8 times total we have checked. So we can say this is okay. Again, we have checked at that position 64 times the split values to find the best split. Okay, so at each level you can say m cross n number of values you have processed to find the best split. How many levels you have in that decision tree? When you have balanced decision tree, so you can clearly or easily find by using log of base 2, as I told you previously, like because of it is binary tree, so that's why log base 2. So number of samples we have, that is m is equal to 16 samples. So by that we can check how many levels in our decision tree. Okay, so at each level we are checking 64 values. Okay, because at each level we have to check 64 values to find best split. So total how many times we will check the values? You can see that you can say in that way 256 times you have checked the split values, 64 split value 4 times. Okay, and when you open that you have calculated here also. Okay, and if you want to write that in the form of notation, you can say that 64 you can calculate by n cross m, which is n is equal number of features, m is number of samples, and how many levels in our decision tree you can calculate by using log of m. Okay, so in that way, which is here 16, you can get you can say a time complexity for the training process of decision tree. Okay, so this you can write in the form of O, which is n cross m into log of m. So this will be the time complexity for the training of decision tree. And when we are calculating the time or space complexity, we are actually calculating we are you can say that we are considering some ideal cases of the model. Okay, so here as this computation and complexity are mentioned in a lot of books, what are the computation and complexity of decision tree, so I thought that it should share with you, so that's why I have designed that session. So in the next session we will see what are the advantages and the disadvantages, or you can say drawbacks of the decision tree. And one of the biggest we have seen that is overfitting, and we also have done a lot of discussion how we can avoid or overcome the overfitting. So for now,